Hey, welcome to AP Chemistry. You're here with Mrs. Mays, and we're going to work through scientific measurement. So let's get started. Measurement is made up of two parts. In every measurement, we've got a number, and you must also have a unit. Numbers without units are unacceptable. Those are called naked numbers, and that's not allowed in chemistry. No nudity in chemistry. And the metric system allows us to use the prefix plus the base unit so that we can simplify our units of measurement. The prefix tells us what power of 10 we need to multiply the number by. So let's see what this is all about. So with metric prefixes, we have all the way from 10 to the minus 24 up to 10 to the positive 24. Now we're not going to use all of those in AP Chemistry. Generally speaking, we're going to hang out in this range from giga to pico. But just know there's lots of other prefixes that are around, and you have this resource that you can go to so that you can look up anything that you're unfamiliar with. Just come here, find this link, and figure out what you're working with. In addition to having metric units, there are certain units outside the international system of measurement that are accepted in the scientific community. So minutes, hours, days, those are acceptable units because sometimes the second is not typically a unit that's large enough for us to work with. Instead of using a cubic meter, liters are commonly used. Even though that's not the base unit for volume, liters are very common. That one we're going to use a lot. So let's focus on the metric system because that's what we'll use most. If we have a base unit, that means it's the type of unit that cannot be derived from other units. And be careful when you're using units because capitalization is important. So with mass, the base unit is not the gram, it's actually the kilogram. And that abbreviation is a little k and a little g. For length, the meter is the common unit. It's the base unit. In time, we measure in seconds, and that's considered for a system of international metric system. That's considered the base unit. Temperature is Kelvin, not Celsius. Kelvin is not in degrees either. It's an absolute temperature, so the abbreviation is a capital K, but we don't put the little degree sign. That doesn't belong next to kelvins. That would go next to Celsius because it's a measure of proportion, but not next to kelvins, which is an absolute temperature. Electrical current has amps, and amount of substance has a unit known as moles. And the abbreviation for the mole is not much help. It's just MOL instead of MOLE. Not much of a shortcut, is it? But that's what it is. We are going to use the units to help us solve problems, and this is called dimensional analysis. So to change the units, we want to use conversion factors that do not change the number, because we can't change the magnitude of the experimental value, but we can change the units. So that means every conversion factor has to be equal to exactly 1. For everything to be equal to 1, we need an equivalent statement first. Like 1 foot is equal to 12 inches. That means if you have a number divided by itself, 12 inches is equal to 1 foot. They're exactly the same, so that means that division is equal to 1. And I could flip it over and it's still equal to 1. No matter how I write it, with inches on the top or inches on the bottom, it's still equal to only 1. So now I can multiply my number by that conversion factor and still not change the number. In fact, I have 2 conversion factors to choose from because I can write it upside down or right side up. So we're going to use whichever one gives us the correct unit in our answer. So we'll look to cross-cancel our units, and we're going to multiply by the one that gets us to what we want. Let me show you what I mean. In this example, we have a Star Trek example. Science fiction often uses nautical analogies to describe space travel. So if the starship USS Enterprise is traveling at a warp factor of 1.71, what would its speed be in knots? Now I purposely did not use metric units here because that would be too easy for you smarties. I'm using crazy units that we don't use much. Nautical units. What? So let's start with what we know. I'm traveling at a warp factor of 1.71. So I'm going to call that 1.71 warp. And then my easiest thing to do is to change that to meters per second, right? So let's go from warp to meters per second by using the information given. Warp is 5 times the speed of light. So 5 times 3 times 10 to the 8th meters per second makes how many warp? 1.71 warp. Well, that's going to make my math easier because 1.71 cancels, and then this unit warp cancels, and now I'm left with meters per second for my units. But I need to get to knots. Oh, how do I get from there to knots? Well, let's see. I need yards per hour, and I have meters per second. So let's focus first on changing meters to yards. Let's do that piece. Since meter is on top here, I need to put it on the bottom next. And then I'll put yards on top because that's what I want to work my way into. So far so good? Now how many meters do we put? Let's find that conversion factor. Here it is. 1 yard is equal to 0.9144 meters. Okay, so now let's get from knots to yards. Let's deal with that first. So if I have 1 knot is equal to 2,000 yards per hour. I can't put another fraction in my denominator, so I'm going to put hours up top. That's where it's going to go when your denominator is in your denominator. It pops back up to the numerator. So now I have knot times hour over yard, and yards goes away, and I have knots times hours. So we've got to get our hours out of the way. You ready to deal with this? Let's take care of the time issue now. So warp has gone, but I still have seconds hanging out down here for meters per second. Meters has gone away. And let's get rid of the hours in the seconds because that's messing up my units. So in 1 hour, how many seconds are there? Right, 3,600, because 60 minutes are in an hour and 60 seconds are in a minute. So now we get to apply the calculator to solve this problem. You ready to do this? We're going to multiply across the top and multiply across the bottom, and then we're going to take the top divided by the bottom because that's what that line there means to do. Divide. Ready for this? I get my calculator and you get your calculator. Get your calculator out. No cheating. Okay, so I'll get my numbers. 1.71 divided by 1.71. I'm not even going to mess with that. Let's start with 5 times 3 times 10 to the 8th. The speed of light. 5 times the speed of light. Don't forget to use your scientific notation with the E button, not the times 10 with a little hat thing. So that's my first step. And then I want to divide that by meters. There's 0.9144 meters in 1 yard. Okay, so I'm going to get that number. Then let's divide by 2,000 yards for the knots. And then multiply by 3,600 seconds in an hour. So there we go. Oh yeah, I didn't do what I said I was going to do. I said I was going to multiply across the top and then divide by the bottom. Yeah, I didn't do that. You know why? Because I just go from left to right and it works for me. 2.95 times 10 to the 9 power. That's how many knots? Woo! That sounds extraordinarily fast to me. But it's 5 times the speed of light. That's why it's science fiction, right? Because we don't actually ever go that fast. So our answer was, how many sig figs do I get to keep here? We started with 3 here. So we're going to keep 3 sig figs. Oh, done. So 2.95 times 10 to the 9 knots. And then if you would, please put a box around your answer so that your grader can find them. That would be super helpful. So now you've seen me use dimensional analysis. It's your turn. I want you to give this a try. Here's your example. We're going to use these crazy units again from horse racing. The Kentucky Derby race is 1.25 miles. How long is this race in rods? And then tell me in furlongs. Then convert that to meters, and then change meters to kilometers. I want to see your answer for each step along the way. And then your final answer, you'll show me in class. Try it, push pause, and you work it through. All right, now that you've worked out that problem, let's move on to a different type of measurement, mass and weight. Mass is the measurement of resistance to change in motion. It's measuring an object's inertia. And weight is measuring the force of gravity on an object. So weight and mass are sometimes used interchangeably, but they mean different things. So don't get too hung up in chemistry if they're asking for the weight and they're talking about an object on Earth. It's probably referring to its mass. Don't get too caught up on that. But you should, of course, understand that the mass of an object cannot change without altering the amount of matter in that substance. So you won't change your mass by going to the moon, unless you pee or something. But that's neither here nor there. The weight of an object depends on the strength of the gravitational field that that object is in. All right. Now let's use some of these measurements to do something meaningful in chemistry. Density is a measure of the ratio of mass to volume. So let's write that simple equation. Density is mass divided by volume. One of my students taught me this little trick. When you do the mass over the volume, you can make it look like a fox. And then if you need to know what the density is, you just ask yourself, what does the fox say? Oh, and then you'll know the density. You can sing in your head if you need to. I'm not going to sing for you. An intrinsic property is one that depends on the identity of the substance. And this is one of the properties of density that makes it the most useful. We can use density to identify something because it does not depend on the amount of substance that is there. Oh, I did that wrong. It's 2 blanks. It's supposed to say how much, whatever. Amount is the same thing, right? So the amount of material would give us like the mass, or the volume might affect the amount, but density is not affected by how much stuff there is. If you have a tiny speck of gold, its density is 19.3 grams per cubic centimeter. If you have a huge mountain of gold, the density is 19.3 grams per cubic centimeter. So as long as the object is at the same temperature, its density is going to be the same, no matter how much stuff you have. So this is useful for the sake of identifying a compound, or to convert your mass to the volume. Let's work through an example where we get to see how this might be used in the chemistry lab. An empty container weighs 121.3 grams. So I'm going to write that down. Underline the important stuff and write it down. So the container alone weighs 121.3 grams. When we fill it with carbon tetrachloride, 4, then we have a density of 1.53 grams per cubic centimeter, and the weight of our container, the total mass, increases to 283.2 grams. We want to know what is the volume of the container alone, so we're going to use the density to get us there. First of all, I need to know how much of the mass came just from carbon tetrachloride. So let's work that out first. So I take my total mass minus the mass of the container, and that should give me the mass of the stuff that I put inside, right? So that's 283.2 grams minus 121.3 grams, and I got 161.9 grams. Go back. 161.9 grams is coming from carbon tetrachloride alone. Now we can use the density of carbon tetrachloride to work out the volume. Density is mass over volume. So I can switcheroo this formula around because I'm going to multiply by the volume and divide by the density. Those trade places. Volume is going to be mass divided by density. I like to move the letters around before I put numbers in, but if you prefer to put numbers in first and then switch things around, I'm not going to be that picky. Go for it. So I have my mass, 161.9 grams, divided by the density was 1.53 grams per cubic centimeter. And remember, a denominator inside the denominator makes that unit move up to the top. So that cubic centimeters kicks up to the top. Now I need my calculator, because I can't do that in my head. So 161.9 divided by 1.53 grams per cubic centimeter. Did you work this out in your calculator? I sure hope so. You better. I'm not the only one working here, am I? Better not be. So I got 105.8 cubic centimeters for the volume of my container. And like a good kid, I'm going to put a box around my answer so that whoever's looking at my paper can find it. So far, so good? Great. You're going to have some homework problems where you work this through. They're the problems in the back of the chapter in the book. Now let's look at temperature, and this will be our last thing for the podcast. Temperature is a measure of the average kinetic energy of all the particles in the object. It's not a measure of heat. Even though temperature and heat are related, it's actually measuring kinetic energy. And as you know, the more heat energy a particle has, the more kinetic energy it has too. We translate heat into kinetic energy. Different temperature units are basically all talking about the same thing. The way we measure temperature all along is the height of mercury in a thermometer, and now we're finding other things to use in place of mercury so that thermometers are safer. So we're going to look at an equation for converting Fahrenheit to Celsius, because I want you to see where these equations come from, and I need you to know it's not that hard. So let's take some reference points. What are some things that we know about Fahrenheit and Celsius temperatures? Like, say, the freezing point of water. We know that water freezes in Celsius degrees at about 0, and at sea level, that is. And in Fahrenheit, we call that 32 degrees. So I can put that point on my graph. There we go, 0 and 32. So draw your graph in your notes right now. Don't wait, do it now. Got it? Now let's make another point. What else do we know? We know the freezing point of water, and I also know the boiling point of water. I bet you do too. What's the boiling temperature in Celsius? And in Fahrenheit? Let's put that point on our graph. 100 degrees Celsius and 212 Fahrenheit. How you like my scale on my graph? That works, doesn't it? Okay, now what do we do when we have 2 points? Let's draw a straight line between them. There you go. So now we have a straight line, and all you smarties know how to write the equation of a straight line. Y equals mx plus b, right? Where y is representing Fahrenheit degrees, and x is representing Celsius degrees. And then b is the intercept of our straight line. So where did we pass through? We put the intercept on there, right? So that's 32. And now we just need to find the slope. Do you remember how to do that? Rise over run. So we're going to put the change in y over the change in x. Oops, x2 minus x1. All right, let's find the change in y. So we went from 100, oh no, that's x. Change in y, 212 minus 32. And then change in x was 100 minus 0. So what's 212? Don't know. 180? Is that right? Calculator time. I hate this. 212 minus 32. Yeah, it's 180. I gotta trust myself. Mental math. Am I the only one who struggles with that? Now let's reduce this fraction. So I have 18 over 10. Let's call that 9 over 5. So that's going in the place of the slope. So to convert Celsius to Fahrenheit, I get 9/5 times my Celsius degrees plus 32. That's the equation for converting. And see where it came from is from this graph of a straight line. All the equations we use in chemistry and physics, they all kind of come from relationships like this, where we can draw the equation of a straight line. Sig figs. Before we go any further, let's talk about this. Sig figs basically expresses how many digits do you get to have in a measurement that are certain, that you know for sure are true. So where the markings are on your instrument, those give you certain digits. And we're going to get into that a little bit more when we talk about precision and accuracy. If you have an exact counting number, those are considered to have unlimited numbers of sig figs. Like if you have 11 soccer players, for instance, we think 11 is going to be counted as 11.00000 because the chances of you having a 0.5 soccer player out on the field is pretty low unless something goes horribly wrong. So counting numbers are considered to have unlimited sig figs. And all non-zero numbers are considered to be significant. The zero is the one that messes us up from time to time. So let's look at when does the zero count and when does it not count. Zeros count when they are between other sig figs automatically. Any zero between other non-zero numbers is significant. So in this number 101, this zero right here would be considered significant because it comes between two non-zero numbers. Any zero that is before the first number is not significant. So if I have 0.0001, then a 01, all of these zeros here are not significant, and this one is because it's between sig figs. I know, it's tough, isn't it? And then after the last number, the zero counts as significant only if it is after a decimal point and the decimal point is written in. So it has to come after a number and after a decimal point. So if I have a decimal, let's say I have 10.01000. Which of these zeros count? Well, we know the zeros that come between the number ones, these are significant, yes. How about these ones at the end? Well, the rule is if they follow a digit and a decimal, then they are significant. So yes, these count. Remember, we have this shortcut to help us keep track of sig figs, the Atlantic side and the Pacific side. So we're going to use Atlantic and Pacific to help us decide if it's significant or not. So if our decimal is absent, as in this number, we're going to start on the Atlantic side of the country and start flying across till I hit a non-zero number. Since I crossed out my zeros, then I have only two sig figs left. Let's look at another one. Now I have a decimal point that's written in, so the decimal is present. I have to start on the Pacific side of the country and fly in until I hit a non-zero number, and I hit one right away. So I have to count all of these as significant. This number has 4 sig figs because the decimal point is written in. Yep, there it is. Okay, now let's look at this one. I have a decimal point. The decimal is present. I'm flying in from the Pacific side then, and I hit a number right away. All of these are significant. I don't get to cross out any zeros. 4 sig figs in that number. So those are the rules for zeros. When we do our labs, we'll be talking a lot more about how many digits are allowed to be in your measurement. Now, when you're working with these numbers, if you multiply and divide, then your answer should have the same number of sig figs in the answer as there are in the least number of the problem you're given. So the least number of sig figs determines the number of sig figs in your answer. But addition and subtraction count these differently. We're looking here for decimal places, not sig figs. So the least number of decimal places is going to determine how many decimal places you get to keep in your answer. So that might complicate your life a bit. So if we did this multiplication, so do the math, 2 times 3 times 0.02, and I'm in scientific notation mode. I have 0.120 as my answer. How many sig figs do I keep? I have 3 here, 2 in this number, and 3 in this number, right? No, 2. Jeez, messing up. 2 sig figs in this number because I crossed these out on the Pacific side. Yep, 2 sig figs. So my answer is restricted to 2 sig figs. I don't get to keep that one. So far, so good? Let's try another one. If I'm dividing, same rule applies. I'm looking at sig figs, not decimal places. So let's do the math first. 1.04 divided by 0.604. Oh my gosh, look at all those digits. How many are we going to keep? That's a bunch of calculator vomit, and vomit does not belong on our paper. I have here 4 sig figs, and here I have 3 sig figs, so my answer is restricted to only 2 sig figs. And I look at the number after my 3 sig figs to see, do I need to round up or not? And it was a 1 after here, so I don't need to round up. Now let's do some addition. In addition, I'm looking at decimal places. So I have 2 decimal places here, 2 decimal places here, but only 1 decimal place in this number. So my answer is going to only get to keep 1 decimal place. So let's work out the math first. 10.01 plus 4.70. Oh, dang it. I messed up. Sorry. 10.01 plus 4.70 plus 0.3. Yep. So 15.01 is the number I've got, but I only get to keep 1 decimal place, so I can't call it 15.01. I have to write 15.0. Should we keep this 0? It's just a 0, right? Do we keep it? Well, I keep 1 decimal place. So yes, you betcha, I am going to keep that 0. If I don't, then in all of the subsequent calculations I do, it's going to restrict my sig figs. So keep it. Don't get rid of those just because it's a 0. Last one, 9.663 minus 0.15. 0.015. Guy, don't listen to me. 9.663 minus 0.15. So 9.513. Do I get to keep all of those? Let's see, I have 3 decimal places here and 2 decimal places here. So I gotta stop after 2 decimal places. So only this piece gets to count. The 3 will be discarded because it's not big enough to cause me to round up in my number. So I can just drop it off. So be careful to round numbers appropriately instead of just truncating numbers by cutting off the end. So don't do that. Just round using the rules of rounding. 5 or greater, round up. Okay, so in class we're going to practice using math and doing math with sig figs. Every time we do a calculation problem, we're going to look at sig figs. Fair? All right, good. Well, we'll see you guys in class.